Bismillahirrahmanirrahim. So welcome to this course EE250 Electric Machinery Fundamentals. My name is Umar Tabrez Shami. I will be teaching sections A and B, and along with this I will conduct the labs of section A. I have already shared the course outline on our WhatsApp group. This group was made recently. One separate group for section B and one separate group for section A. So those of my students who who are not a member of any group, they may join or they may contact the CRs of section A or section B and request to join the group as per your sections. So I will on the WhatsApp group, I will be sharing important files. For example, the course outline, for example, our any course material, or if there is any important announcement, I will use the WhatsApp group. So I have already shared the course outline, the OBE course outline. This course outline includes the lecture plan for electric machinery fundamental theory. It also includes the laboratory experiments for this course. So I hope all the students, they have seen the lecture plan. So now we come to our first chapter. In this course, we will follow two books. Both books have been mentioned in the course outline. However, in today's lecture, we will follow this book which is being shown on the screen. The title of the book is Electric Machinery by Frisgerald and Kingsley and Oomans, and I am using the 7th version or the 7th edition. We are going to study the chapter number 1 of this book. The chapter number 1 and all of the slides that will be shown, inshallah, that will be shown in this presentation or in this class. All of the slides have been made from the same book. Okay. So we are going to start with chapter number 1. The chapter number 1 title is Magnetic Circuits and Magnetic Materials. I would like to cover the article number 1.1, article number 1.2, 1.3, 1.4, 1.5, and 1.6. So these are the 6 articles that I want to cover, inshallah, in this chapter, from this chapter. सबको मेरी आवाज आ रही है क्लियर, यानी कि कोई हल्की तो नहीं आवाज आ रही?
क्लियर?
यस सर, आ रही है।
चलिए जी। तो इस दूसरी बात यह है कि इस क्लास में सेक्शन ए और सेक्शन बी वाले हैं, तो कोई रिपीटर्स भी बैठे हैं?
यस सर, आई एम रिपीटिंग।
So there are repeaters also?
Yes sir.
Okay, most welcome. Okay. So my message to the repeaters is that please also join either section A WhatsApp group or section B WhatsApp group. I would prefer that to join section A WhatsApp group. The repeaters may contact the CR of section A and request to join the WhatsApp group, because I have already started to share many files. We created this group yesterday so that we can save time and share all the data files on the WhatsApp group. So the repeaters, please join our WhatsApp group, most preferably section A. Okay, so let us now start. This is our first article, Bismillahirrahmanirrahim. Article number 1.1, the introduction to magnetic circuits. This chapter is very simple. It is very interesting. We will discuss magnetic circuits because magnetic circuit we will be using in AC machine, electric machinery. That is, in this, we would like to discuss DC motors, DC generators, AC motors, and synchronous generators, and also transformers. So these are our five main fundamental electric machinery. All of them use magnetics. So therefore, our first chapter, naturally, it will be magnetic. It will be a chapter on magnetics. So in the introduction to magnetics, by definition, a magnetic circuit consists of a structure composed for the most part of high permeability magnetic material. The presence of high permeability material tends to cause magnetic flux to be confined to the path defined by the structure, just like currents are confined to the conductors of an electric circuit. So one terminology that we see is magnetic circuit. What is magnetic circuit? Magnetic circuit is the path. Magnetic circuit will be the path through which magnetic lines of force or magnetic flux lines, they can pass easily. Okay. Second is what is a high permeability magnetic material. A high permeability magnetic material is a material which can allow magnetic flux lines to pass through it very easily. That is called a high permeability magnetic material. Most of the time, the ferromagnetic materials, they are called high permeability magnetic materials. Ferromagnetic materials, for example, iron or steel, they will allow they will allow flux to pass through them very easily. On the other hand, we have air. Air is not a high permeability magnetic material. It does not allow flux to pass through it very easily. Yes, flux can exist in air, but the flux faces a large resistance, as we will see in a later slide. Okay, so next is that in the magnetic structures or in the magnetic circuits, the flux, they pass or they flow through a certain path which is defined by the structure. The flux line will pass through the material defined by the structure of the material. So in this example, what we see is we see a magnetic material. It can be of iron, it can be of silicon steel. Now the shape of the magnetic material defines the path of the magnetic flux. This is very important to note that whatever is the shape of the material, the flux line will also follow the path according to the shape of the material. And after this, like an example is given that like current passes through electric circuits through the conductors, likewise the flux will pass through the material that is defined by the shape of the material. So in this diagram, what we see is we see the gray color shaded material. It is our high permeability magnetic material. Then there is the flux lines. Now these flux lines, they are not produced automatically, they are produced by a winding. So what we see is we see the source from where the flux is coming from, and it is a coil. it of n number of turns, and when current passes through the coil or through the n number of coils, as a result, flux is produced. This flux produced and the direction of flux produced is found by using the well-known right hand rule that defines that if the fingers of the right hand they curl in the direction of the current, then the direction indicated by the thumb indicates the direction of the flux. So in this diagram, we have the n number of turns through which current I is passing, and as a result, we get n into I, which is called the magnetic flux intensity H. It produces the flux according to the permeability of the material, and then there is the mean core length, that is the mean or the average length the flux covers, and then there is the cross-sectional area of magnetic material, AC. This is the area through which the flux will pass through. And then we have the magnetic core permeability, mu. It is a relative quantity. It does not have any unit. We multiply mu with mu naught. Mu naught is the permeability of free space. And it has a value 4 pi to the power minus 7 permeability of free space. Anyways, we will do a example where we will see the exact value of mu naught. So permeability mu will be multiplied by mu naught, which is the permeability of air. Okay, G. So yes, here it is. Magnetic permeability is mu of the material, and mu of the material is much larger than mu naught. Mu naught is 4 pi to the power minus 7. Unit is Henry per meter, is the magnetic permeability of free space. Mu naught represents the magnetic permeability of free space. And high permeability material are those material whose mu value or permeability is much larger than 4 pi to the power minus 7 Henry per meter. So how do we find the permeability of a given material? We multiply the relative permeability of the material with mu naught, and we get the exact permeability of a material. Now, in this diagram, the core is of uniform cross section and is excited by n turns carrying current I. This winding produces a magnetic field in the core as shown in the figure. So yes, as we have discussed in the previous slide, that this flux of line, they are not produced automatically. They are coming from a source, or we have to do work, or we have to expand energy. And that is that when we multiply the current flowing through the coil with the number of turns, then we get a magnetic field. Now the product of Ni, that is number of turns and current, is called MMF, the magnetomotive force. This is the magnetomotive force applied to the magnetic circuit. It is simply a force. It does not define the value of flux. The value of flux will be found by considering the level of permeability of the magnetic material. If the permeability is high, then we will have high flux. If the permeability is less, then we will have less flux. Okay, now the net flux crossing surface A is given by B dot A integral of S, which is which is, that is, we multiply the area with the flux density. B here represents the flux density, the flux per unit area. We multiply the flux density with the total area, we get the flux, and the flux unit is always Weber. The unit of flux is always Weber. Maybe most of students have studied this during college level, but we are just going through this to we will go through this, and then we will look at a number of examples. But there will be some additional concepts to be shown in this lecture, inshallah, also. Okay, so flux is the magnetic density multiplied by the area, where in this equation number 1.4 represents the flux and the unit is Weber. Right, now equation number 1.5, it tells us the relationship between MMF acting on a circuit and the magnetic field intensity in that circuit. That is, MMF is equal to N into I is the integral of H dl. H, what is H? H is the magnetic intensity. B was the magnetic density, whereas H represents the magnetic intensity. Now, what is H? Is H a scalar value or is H a vector? Yes, will somebody answer? What is H? Is H a scalar quantity or is H a vector quantity? अच्छा, ये आप सब देखें कि इक्वेशन नंबर 1.5 ये क्या है ये? It is the magneto MMF value. It is the relation of MMF and the flux intensity and the dl, small portion of the length. dl represents the path length or a small portion of the path length, and the line integral of equation 1.5 becomes simply the scalar product of magnitude of H and the mean flux path length LC. So H is a vector. However, in equation 1.5, we will consider only the magnitude of H. We will consider only the magnitude of H. Can somebody tell why H is vector? Because H always has a direction. H always has a direction. So therefore, our equation 1.5 can be simplified that the MMF is equal to N into I is equal to H into LC, where HC is the average magnitude of H. And what is LC? LC represents the mean core length. Mean core length. So what is this mean core length? Let us go back to our diagram. That in this diagram, here is the mean core length. This is LC. This is the LC. What is LC? LC is the average distance covered by the flux in our magnetic material. So LC represents the mean or the average length covered by the flux in the magnetic material. Why are we considering the length? Because as we stated that the flux line, they always follow the structure path of the material. So whatever is the structure, whatever is the structure of the material, the flux line, they will pass through that well-defined material path. And the length that our flux will cover, it will be used to define the MMF. That is the H intensity, that is the magnetic field intensity multiplied by core length. H is also H, the value H or the magnetic field intensity is also called our magnetic field strength. Magnetic field strength. Now, the relationship between magnetic field intensity and the flux density is shown in the very well-known equation B is equal to mu times H, equation number 1.7. So B is equal to mu times H. So इस equation में in equation 1.7, what is the independent value and what is the dependent value? In equation 1.7, who will tell us? I want students to answer. In equation 1.7, what is who is the dependent factor and who is the independent factor in equation 1.7? It's very simple.
B is the dependent factor.
Mu is the dependent factor and H is the independent factor.
ठीक है?
बी जो है इंडिपेंडेंट है,
तो
ये
ये सब
डेंसिटी
जरा
ऑफ मटेरियल.
हाँ, जरा प्लीज सब इधर देखें कि इन इक्वेशन 1.7 H is independent. H defines B. B is a function of H. B is dependent on H. What we see on the left hand side is B, that is the flux density, and what we see on the right hand side is H, magnetic field intensity. So the answer is that H, the magnetic field intensity H is independent. It will define the B value. B is H is independent, B is dependent on H. B is a function of H. What is a function? The function is mu times H, simple function. However, equation 1.7 tells us another story that B is a linear function. However, in practical, we observe linearity, but in a certain limit, but in a certain area. After this area, the formula is invalid. This formula 1.7 is invalid. We observe non-linearity after a certain limit. So when we discuss the graph of B and H, we will see that this equation is not valid always when placed in magnetic materials. However, this equation is valid always for all times when placed in free space. This equation simply tells us that as we go on increasing H, we will also go on increasing B. However, in magnetic materials, for example, iron, silicon iron, this is not the case. These irons, they tend to saturate, and when the irons they saturate, after saturation, equation 1.7 is not valid anymore. So this equation is valid up to certain limits, but when the material is saturated, it becomes invalid. However, while dealing in free space, we will observe this equation to be true for all times. Okay, so B is equal to mu times H, and B is equal to flux over area. F is the MMF, the magnetomotive force, and it is the NI, that it is a product of number of turns and the current flowing through the winding. Right. So another slide full of descriptions, full of formulas. That is magnetic circuit with air gap. Magnetic circuit with air gap. Let us consider a magnetic circuit with two series components, both carrying the same flux phi. A magnetic core of permeability mu, cross-sectional area AC, and mean length LC, and an air gap of permeability mu naught, cross-sectional area AG, and such that the air gap length is G, and it is very small. So what we are going to discuss refers to diagram as shown in this slide. In this slide, we see a magnetic material. It is mostly composed of iron or of a material of high magnetic permeability. And then there is also a very small air gap. The length of the air gap is much smaller than the length of the magnetic material. We represent the air gap with the value G. Whereas the length of the material, magnetic material, is represented by value LC. The area, cross-sectional area of the core is AC, AC area of core, and the area of the air gap is represented by AG. And then also mu represents the permeability of the core, whereas mu naught represents the permeability of the air. Now, why did we see that they are two series connected? How can we say that the magnetic circuit with two series components, both carrying the same flux? This statement is valid because the flux passes through the core, and then the same flux passes through the air gap. So for the flux, the magnetic core, permeability mu, and the free space air are both in series, because whatever flux flowed through the magnetic core, the same flux also flows through the air gap. Therefore, the magnetic material and the air gap are in series. Now, for this given diagram, what is the flux density in the core and what is the flux density in the air gap? The flux density in the core is defined by BC, that is mu. That is, mu is the total flux divided by area of the core, and then the flux density defined by air gap, or in the air gap, is defined by mu times or mu over AC. It should be AG. This should be AG. So students, please note a correction in equation 1.9. That is, the flux density of the air gap is mu over AG, not AC. AC is the area of the core. AG is the area of the air gap. We are using air in equation 1.9. We want to use the area of the air gap AG. Okay, so what is equation 1.10? Equation 1.10 is very important as it tells us the total magnetomotive force required to produce flux in the core and in the air gap. Therefore, Ni, or the MMF, the magnetomotive force, is equal to HCLC plus Hg into the length g. This equation, this very important equation, tells us that if we want to produce flux in a magnetic material with an air gap, then we will have to consider the MMF required to produce flux in the core plus the MMF required to produce flux in the air gap, and we add them together and we get the total MMF. This total MMF must be provided by the source, which is a coil of certain number of turns and a certain amount of current is flowing through the coil. So equation 1.10 defines the total MMF required to produce flux in the system. And this system, when I say system, I mean the magnetic material with the air gap, because they are two things in series. These are two components in series. Okay, so using linear BH relation, as shown in equation 1.7 gives that the MMF is equal to flux density of the core divided by mu into L plus flux density of the air gap divided by mu naught into the air gap. And then in terms of flux, if we take flux common, then we get that F, or the MMF, is equal to mu times LC over mu AC plus G over mu naught AG. अब ये जो this equation 1.12, it leaves us with two very important definitions. What is this? It is called the reluctance. LC, the component LC over mu AC, is the reluctance of magnetic core, whereas the component G over mu naught AG is the reluctance of free space. This is the mathematical definition of reluctance of core and reluctance of free space. Now, the question is, what is reluctance? Reluctance is, simply put, the resistance faced by the magnetic lines of force. That is called reluctance. Reluctance is the opposition, it is the resistance faced by the magnetic lines of force when flowing through a certain material. Like, for example, like we have our electric resistances, like we have our electric resistors. These resistors are the value, these are the resistance, these are the opposition faced by current. Similarly, reluctance is the opposition in the material, or reluctance is the opposition in the system faced by the flux. In our system, we have two components, the magnetic material and the air gap. Therefore, the flux will face two oppositions. First opposition will be of the magnetic core. It is labeled as, it is called as reluctance of the magnetic core, and the second opposition is faced by the free space, is that the magnetic lines of force will face resistance or reluctance of free space. Okay, so reluctance is the opposition faced by the magnetic lines of force. Now, my question is, in our given system, as shown in the diagram, which component will present large resistance to magnetic flux? The magnetic core or the free space?
Magnetic core.
Free space.
हाँ जी, so any more answers? दो आंसर्स आ गए.
Free space.
Free space.
ठीक है, Okay, so in this system, the largest resistance or opposition presented will be of the air gap. Why? Because the mu naught is smallest, or the permeability of free space is very small. Therefore, very, very small flux as compared to the core. And the core, it will present the minimum reluctance. ये आपने बात अच्छी तरीके से समझ लेनी है. क्या बात है? That is, the components which have high magnetic permeability, they present minimum reluctance of magnetic core. They present the least or less resistance to flux. And those components that have very small permeability, they present large resistance, they present large opposition for the flux. So the answer is that the free space component, it will present large resistance, whereas the magnetic core, which already has very, very large permeability, it presents the least resistance, it presents the least opposition to flux. So in general terms, flux will very easily pass through the core. However, flux faces difficulties when passing through the air. This is the conclusion of this slide. And secondly, ये आप जरा note कर लें. Please note that the symbol used for reluctance is slightly different from R. Okay, so I would like all the students to follow this scheme also, to follow this symbol also. It is not the perfect R. It is slightly modified, used in some Greek alphabetical symbols. So any questions so far? Okay, so let us now come to the next slide. We used the term resistance. Resistance means opposition. In general terms, by general definition, resistance means opposition or difficulty. However, in electric circuit, resistance means the difficulty faced by current while flowing through an electric circuit. Okay? Now, so this means that we can create an analogy between magnetic circuit and electric circuit. And this is what we are going to do in this slide. In this slide, we will develop, or we will try to develop an analogy or a similarity between magnetic circuit and electric circuit. Okay. So we'll start with equation number 1.13. This is RC, or this is the reluctance of the core. Reluctance of the core is given by LC over mu AC, and then equation 1.4 is the reluctance of the free space given by G. G is the length of the air gap. G is not gravity, it is the length of the air gap only. Okay, so 1.14 reluctance of free space is G over mu naught Ag. And then from equation number 1.12, ये जो इक्वेशन है, दिस इक्वेशन नंबर 1.12, इसमें आप LC over mu AC को reluctance of core से replace कर दें, or and we can replace G over mu naught Ag with the reluctance of free space. What do we get? We can recreate 1.12 into equation 1.15. That is, the MMF is equal to mu into reluctance of core plus reluctance of free space. And then this simply tells us that by rearranging equation 1.15 for mu is equal to MMF divided by the sum of two reluctances. Equation 1.16. And then we already know that reluctance of the core is LC over mu AC, and reluctance of free space is G over mu naught AG. This means that the is flux can be found given in equation 1.7. अब आगे जो now the component 1.12, it starts with the assumption, or it starts with the reality, not assumption, the reality that since mu or probability of core is much larger than probability of free space, therefore the reluctance of free space is much larger than the reluctance of core. Therefore, this equation, reluctance of free space is much larger than reluctance of core. If we establish this, then we can say that we can ignore the LC over mu AC. इसको आप ignore कर दें, and then we get that flux is simply the MMF over reluctance of free space. That is, flux is Ni into mu naught Ag over the length of the air gap. Equation number 1.12. This is an approximation, but we established this approximation with the fact that the reluctance of air is much larger than the reluctance of the core, because the permeabilities of the two materials, they are different. Now in the diagram, what we see is we see a similarity of electric circuit versus magnetic circuits. On the first hand side, on figure A, we see an electric circuit. It consists of a voltage source V. It consists of two resistances R1, R2, and then a current flowing through R1 and R2. Now, R1 and R2 are both in series. Therefore, the current can be found by dividing the voltage by the sum of resistances R1, R2. On similar terms, for the circuit, for our magnetic circuit, we have magnetomotive force, Ni, MMF as the source of flux. Then there is the flux which will pass through reluctance of material, magnetic material, and the reluctance of the free space. Therefore, the reluctance of core and reluctance of free space both are in series, and the flux, it is defined by the value of Ni, or that is the value of magnetomotive force, divided by the reluctance of core plus the reluctance of the air gap. So we see that we have we have similarities between the magnetic circuit and electric circuit. And what is the advantage? That we take this to the advantage that we can solve our magnetic circuit using same formulas of electric circuit, which will make easy for us to calculate values. And this is what we are going to do, that we will transform the magnetic circuit into electric circuit, solve using the formulas, the nodal equation, or the KVL, or the Kirchhoff KCL, to solve for electric circuit, and then find the values from magnetic circuit. So this is the advantage of our given scheme. Now, another important concept that we must discuss in the same diagram, that in the diagram we saw air gap. However, we must not forget that flux, although flux will pass through the air gap, but 100% flux will not pass through the air gap. We will have certain amount of flux that will pass through the corners of the air gap. And this takes us to another important concept, that is fringing. Fringing. Fringing is a term which is used to describe the path of the flux that does not pass through the flux core. However, it takes an alternate path and reaches to the other side This is called fringing fields. So what we see in this system is that we have a magnetic core material through which flux is passing, and then we have an air gap. Here is the air gap. This is the air gap. We have free space. So 100% of the flux do not pass through the air gap, or they do not pass vertically through the air gap to reach the second part of the core. Some portion of the flux, they take an alternate path and flow from the other side into the other part of the core. So we must ensure that the effect of these fringing is to increase the effective cross-sectional area AG. So what is the impact? The impact is, or why are we discussing this? We are discussing this so that the students, they can keep in mind that whenever there is an air gap, the effective cross-sectional area of the air gap increases due to the fringing. So we can always ignore this, but it is always better to keep in mind that the air gap area is not strictly the area of the core. It will be slightly larger due to the fringing effect. So the effect of these fringing field is to increase the effective area, cross-sectional area AG of the air gap. Various empirical methods have been developed to account for this effect. So we can find the effective area, including fringing, using empirical methods. What is empirical? What is the meaning of empirical? Empirical means that there is no derivation. It's just a formula that people have derived using their experience. So there is no mathematical derivation. It's just a formula that people have come up with using their experience. Okay जी. So let us now come to example number 1.1. तो सबको समझ आ रही मैं क्या कह रहा हूँ?
Yes, sir.
Yes, sir.
ठीक है जी. तो दूसरा ये है कि if there is any question, students please do not hesitate to answer to ask the questions. So I will try my best to answer those questions. Okay. Okay. So example number 1.1 statement is very simple. The magnetic circuit shown in figure 1.2 has dimension AC is equal to AG is equal to 9 centimeter square. G, which is the air gap length, is 0.05 centimeter. The effective core length is 30 centimeter and N is equal to 50 ton. Assume the value of mu R, that is 70,000 for core material. So this core material has a mu of, or permeability of 70,000. It is unitless. Remember that it is unitless. It is a relative term. It does not have any unit. Okay. For part A, find reluctances of the core and the gap for conditions shown that magnetic field is operating with the flux density is 1 Tesla and find B the flux and the current I. Okay, ji. So first of all, let us find the reluctance of core and reluctance of the gap. We can find the reluctance of the core and reluctance of the gap by using equation number 1.13 and 1.14. और ये जो है this we are using equation 1.13 over here and to find the core reluctance and we place in the values. LC, we need LC. LC is the effective core length. It is 30 centimeter. We convert them to meters and then mu r into mu naught into the AC. AC is the cross sectional area. We get reluctance equal to 3.79 to the power 3 ampere turns per Weber. Now we come to the reluctance of the gap. Reluctance of the air gap using the same formula. We will find the reluctance of the air gap equal to 4.44 to the power 5 ampere turns per Weber. Now the part B is the total flux. How do we find the total flux? Flux is equal to flux density multiplied by the cross-sectional area. Flux density multiplied by cross-sectional area. So flux density is 1 Tesla and AC is the flux, is the area, cross-sectional area. We multiply the cross-sectional area with the flux density, we get 9 to the power minus 4 Weber. And then we have the current. Current कैसे find करेंगे? Current is equal to the MMF is equal to N into I. And also MMF is equal to flux into reluctance of core plus reluctance of the gap, air gap. Right? So we equate them together. We equate these two equations. That is N into I is equal to flux bracket RC plus RG. And then current can be found by I is equal to flux bracket RC plus RG total divided by number of turns. And this is what is going on in our part number C. That is current is equal to MMF divided by number of turns. MMF is given by flux into RC plus RG, same formula, divided by number of turns. And flux is 9 to the power minus 4 and this is the total sum of both reluctances. That is 4.46. That is apne in dono ko we can add them together. We can add these two reluctances together and we get 4.46 to the power 5. This is the total reluctance divided by 500. Why 500? Because 500 is the number of turns. 500 is the number of turns. So the current will become 0.8 amperes. So my dear students, in this example, the example was very simple. There is no complication in this example. But what I would like all the students to remember is that whenever we are performing examples or numericals, please do not ignore the units. We must never ignore the unit at any stage. So you must be very clear of the units and you must also write the units at every step. So any questions related to this example? Okay, so now let us proceed. This is a practice problem 1.1. It is based on example 1.1. So I would like the students to perform practice 1.1 on their own during their free time. I will now proceed to the next slide. This is example 1.2. The example 1.2 states that the magnetic structure of a synchronous machine. Synchronous machine is a machine that converts electric energy to mechanical energy, or it is a machine that can convert mechanical energy into electric energy. It can be used as a motor or as a generator. So the question is, example 1.2, the magnetic structure of a synchronous machine is shown schematically in figure 1.1 for 1.5, assuming that rotor and stator have infinite permeability. Mu is very, very, very large. Find the air gap flux and flux density Pg. Flux density of the air gap. For this example, we can take current equal to 10 amperes, number of turns N equal to 1000 turns, and the air gap is 1 centimeter. And the area of the air gap is 200 centimeter square. Okay, ji. So let us do some mind thinking over the statement. Statement क्या है? In the statement, we see a line which states that iron stator has infinite probability, that is mu tends to infinity. इस बात का क्या मतलब है और इस बात में ऑथर आपको क्या हिंट दे रहा है? यस, कौन जवाब देगा जी?
सर हम स्टेटर और रोटर की रिलक्टेंस को इग्नोर कर सकते हैं, ये वो कहना चाह रहा है कि वो जो फ्लक्स है वो सिर्फ एयर गैप की रिलक्टेंस पर ही डिपेंड करेगा.
So yes, so first of all, by this statement, we did not get any specific number of the stator and rotor magnetic permeability. ठीक है, जो स्टेटर है वो भी आयरन का पूरा बना हुआ है, नो एयर गैप इन द स्टेटर, और ये जो रोटर आपको नजर आ रहा है, इट ऑल्सो हैज परमेबिलिटी ऑफ म्यू टेंडिंग टूवर्ड्स इंफिनिटी. Stator also has permeability tending towards infinity. So no value of the stator permeability or rotor permeability is given. So this means that we can use equation 1.20, where we can ignore the reluctance of stator and rotor, because उनकी जो म्यूज हैं वो infinite है. If mu becomes infinity, if mu इस equation 1.17 में देखें, अगर mu जो है वो infinite हो जाए तो ये पूरी टर्म क्या लीड हो जाएगी, किधर चले जाएगी? It will tend to 0. समझ आ रही बात सबको? If we take mu as infinity, then this complete term is LC over mu AC. This complete term will tend towards 0. Hence, we can ignore this term of the core, and we can find the flux by simply dividing the MMF with the reluctance of the air gap. So we are going to use equation 1.20 in example 1.2. So notice that the two air gaps in series of total length 2g. ठीक है, अच्छा, अब दूसरी बात कि ये जो एयर गैप है, this air gap is 1 centimeter, and the air gap on the top, it is also 1 centimeter. So the total air gap is 2 times g, that is 2 centimeters. and that the symmetry of the flux density is equal. कि symmetry of flux equal से क्या मतलब है कि देखिए जब रोटर में से फ्लक्स पास होगा then 50% of the flux should flow on one side and 50% of the flux should flow on the other side. That is the meaning of symmetry of the flux. Since the iron permeability is assumed to be infinite, its reluctance is negligible, that is equal to 0 or almost equal to 0. And we can then use equation 1.12. And equation 1.12 leads us that the flux is equal to Ni mu naught Ag divided by the total length, which is equal to 12.6 milliweber. And we divide this flux by the cross-sectional area of the air gap, because we have to find the flux and we have to find the flux density. Therefore, we divide the flux with the air gap area, that is equal to 0.630 Tesla. And in this example, we are also ignoring the fringing effect. The fringing effect will be here, but since the area of the air gap is given, therefore we will use this area to find the flux density. So what is the conclusion of this example? एक तो ठीक है, what we have solved the problem, but what can we conclude from this example? There are two important conclusions from this example. First conclusion is that whenever there is a rotating path, then the flux should be divided using a symmetry. ये आपका पहला conclusion है. That is, when we have a rotating path and when the flux passes through the rotating part into the stator, then the flux should be divided in a uniform or equal symmetry. This is the first conclusion. The second conclusion is that the dominant reluctance is due to the air. The reluctance of the stator, the reluctance of the core is very, very small, and in we can sometimes ignore, or we can sometimes negate or negligible the reluctance of the core. However, the dominant reluctance is always of the air, and we have to take into account the reluctance of the air. So these are two important conclusions from example 1.2. So then there is the practice example, which is almost similar to example 1.2. So I would like the students to repeat them using practice example 1.2. The solution is also given. Okay, now we come to article 1.2, that is the flux linkage. Flux linkage, inductance, and energy. So for flux linkage, we will start with the Faraday's law of electromagnetic induction. It states that EMF induced in a coil is equal to the rate of change of flux linkages. Flux linkages क्या होते हैं? Flux linkages are those flux that are linking or that are physically touching the coil. And the voltage induced is always given by the formula d phi over dt. N d phi over dt, or where n is the number of turns and d phi is the rate of change of flux and dt is the rate of the time. D lambda is equal to n d phi. D lambda here represents the flux linkages. Those are the flux that are physically touching the coil, and d lambda is equal to n d phi divided by the dt. where lambda is a flux linkages and lambda is defined by number of turns multiplied by the flux. Number of turns multiplied by the flux. It is lambda means that certain amount of flux for phi amount of flux links n amount of coils. That is the lambda. And the unit of flux linkages is very simple, Weber turns. Weber for the flux and turns for n, that is the number of turns. So lambda is equal to n phi, unit is Weber dot turns or Weber multiplied by turns, Weber turns. Now, the Lenz's law and the Faraday's law. In the Faraday's law, we define the amount of voltage induced, and this is given by EMF is equal to minus n d phi over dt, where n is the number of turns, flux is the flux, magnetic flux, and dt is the portion of the time. Now, what is this minus sign? This minus sign represents the polarity of voltage being induced. The minus sign represents the polarity of voltage being induced. It tells us very important thing of voltage being induced, which was defined by the Lenz's law. So the minus sign is in fact contributed by the Lenz's law. And it states that the Lenz's law, the induced B field in a loop of wire will oppose the change in magnetic flux through the loop. So the voltage being induced will be of such polarity so that when current is allowed to flow, this current will produce another flux which will cancel our main flux phi. To cancel this flux, we will have an EMF produced in such a direction or in such a polarity so that when current passes, a flux is produced which will eventually cancel the main flux. And this is defined by the Lenz's law. So in EMF, we have the minus n d phi over dt. The minus sign represents the Lenz's law. It defines that what will be the polarity of the induced EMF so that when current is allowed to pass, then the current will pass in such a direction so that to cancel the main flux. और यहाँ पे एक डायग्राम दिखाया गया है कि जो we have a changing field, and then the coil produces a flux in such a direction to cancel the main flux. However, this flux produced by the coil will not be random, it will be the result of a current, and that current must flow in a certain direction in order to produce a flux in the opposite direction. So the minus sign is in fact the Lenz's law that describes the polarity being defined. याद रखें कि it is never, ये ना समझे कि हमेशा नेगेटिव होता है. अगर आप एक नेगेटिव वोल्टेज दे रहे हैं तो then the flux will produce an EMF on the coil which will be in the opposite direction, so that the flux being produced will also be in opposite direction and to cancel the main flux. So this was given by the Lenz's law. Now in the next slide, what we have is the definition of the flux linkages and the inductance. So inductance is simply put the flux linkage divided by current. The inductance of a coil is flux linkage divided by the current, and it is represented by the alphabetical letter L. L is equal to lambda over I. Whereas lambda क्या था? Lambda was the flux linkages. We can substitute, or we can use equations 1.5, 1.18, and 1.27. 1.15, 1.18. This is 1.15, 1.5. Magnetomotive force is equal to N into I. Then 1.18. And then there is the equation 1.27, which leads to inductance is equal to N square over R, or N square over total reluctance. So the inductance is a function of the number of turns of the coil and the reluctance of the magnetic path. ये आपने इक्वेशन नंबर 1.29 इसको आपने कभी नहीं भूलना. It defines the relationship between the number of turns and the geometry of the magnetic material, और इसको आप बोलते हैं इंडक्टेंस. इंडक्टेंस कॉइल की होती है, जो कॉइल आप इस्तेमाल कर रहे हैं, जो सोर्स है फ्लक्स का, इंडक्टेंस हमेशा कॉइल की होती है. और वो क्या होता है? एट दैट इज इक्वल टू नंबर ऑफ टर्न्स ऑफ द कॉइल डिवाइडेड बाय द टोटल रिलक्टेंस इन द मैग्नेटिक सर्किट. ठीक है, ओके. एक बात ये क्लियर होगी. दूसरी बात ये है कि हमने अभी देखा है in our theory and example 1.2 that the reluctance of the core is sometimes negligible. We can ignore the magnetics of the core if the probability is very large or tending towards infinity. In that case, we come to equation 1.30. In that case, where we can neglect the reluctance of the core and we only consider reluctance of the air. In that case, our inductance becomes n square over mu naught Ag divided by the air gap length. So we, in this equation, we are ignoring the magnetic path because magnetic path is offering very small reluctance or resistance to the flux, and majority of the reluctance is coming from the air gap, so we only consider the air gap. And inductance is then becomes n square over mu naught Ag over the air gap length, and the unit of inductance is expressed in Henrys or Weber turns per ampere. Weber turns per ampere. So the unit of inductance is Henry, or we can also write it as Weber turns per ampere. Now we have a example, और एक और चीज मैंने करानी है, वो है कि magnetic energy stored. The total stored energy, the stored energy is given by formula half Li square. This is the total magnetic energy stored. It is given by half Li square, and where L represents the inductance, I represents the current in the inductance, and when we take the magnitude, or when we take the product of half Li square, we get the total energy stored in a magnetic field is equal to the work done needed to produce a current through the inductor. Right, now we come to a example number 1.3. The statement is very simple. The magnetic circuit shown in figure 1.6 consists of n number of turns on a magnetic core of infinite probability with two parallel paths G1 and G2 and areas A1 and A2 respectively. Find A, inductance of winding, B, flux density in G1 when winding current is I, neglecting fringing effect in the air gap. So in this example, we will make use of magnetic circuit being transformed into electric circuit. हमने इस example को solve करना है using concepts of electric circuit. So what we will do is we will transform our magnetic circuit into electric circuit and then solve the electric circuit. वो कैसे? वो ऐसे कि आप इस डायग्राम को देखें. We have a magnetic core. On the first leg there is n number of turns through which current is flowing. We get mmf. This mmf will become the source, or इस electric circuit में here is mmf n into I. Okay, then there is the core, magnetic core, but in the statement the permeability is infinity, therefore we can neglect the reluctance of the core and only focus on the reluctances of the two air gaps G1 and G2. राइट नाउ अगर आप इसको फिर इस पाथ को सिर्फ एक सिंपल एक पाथ ही समझें और उसका रेजिस्टेंस ऑफ द पाथ को जीरो कर दें, देन वी विल हैव स्ट्रेट लाइंस. स्ट्रेट लाइन लाइक ये जो स्ट्रेट लाइंस हैं ये क्या शो कर रहे हैं? दे आर शोइंग दैट द पाथ ऑफ द कोर it has infinite permeability, so that the reluctance is almost zero, and therefore we are ignoring the resistance or reluctance of the air magnetic core material. Then we will consider the reluctances of gap 1 and gap 2. Here we have reluctance 1 and reluctance 2, which represent the reluctance of air gap 1 and air gap 2. Both of the air gaps are unequal, G1 and G2. Therefore, we have two reluctances, reluctance 1, reluctance 2. Now they are in parallel. Reluctance 1 is in parallel reluctance 2 because looking at the geometry of the magnetic circuit. So in reluctance 1 we will have flux 1, in reluctance 2 we will have flux 2. The mmf being provided is equal. Same mmf is being provided to reluctance 1 and same mmf is being provided to reluctance number 2. This is the concept from the electric circuits. So now let us solve our example. That is, कोई values नहीं given, no values are given, so we will solve in a generic, for a generic purpose. That is, flux is Ni over the total reluctance. ये जो पहला equation है, ये equation कहाँ से आई? This equation we have got from here. mmf is equal to flux multiplied by total reluctance. So flux is divided by total. Now total reluctance अब कैसे find करेंगे? Total reluctance इस case में आपके पास दो resistances हैं which are in parallel. So we will use the parallel equivalent circuit concept. That is R1 over R1 into R2 R1 into R2 divided by the sum of R1 and R2. R1 is G1 over mu naught A1, R2 is G2 over mu naught A2. We place in the equation, we get the total flux, and then find the inductance. Inductance का क्या formula है? Inductance is N phi over current. N phi is N into the flux, which will be found over here, and flux n square over bracket R1 R2 divided by R1 multiplied by R2, and therefore the inductance becomes mu naught into n square bracket area 1 over G1 plus area 2 over G2. So this is the inductance of the given magnetic circuit. In the second part, we have to find the flux in we have to find flux density in 1 and this flux density ये हम कैसे find करेंगे? That is, we have the flux phi 1. Phi 1 कैसे find करेंगे? Phi 1 ऐसे find करेंगे कि mmf divided by reluctance of air gap 1 Ni over R1, and then this gives us the total phi 1. Phi 1 को आप divide कर दें by A1, which is the area of gap 1, we get the flux density in area 1. इसी तरीके से अगर आपने phi 2 का flux density find करनी है, then we take phi 2 and divide by the area of phi 2 and we get the flux density of phi 2. So this example is generic. There are no values given. Simply we have kind of derived formulas for this given structure. So now अब टाइम कितना रह गया हमारे पास?
सर दूसरी क्लास है सर हमारी।
दूसरी क्लास शुरू हो
ठीक है जी. So I will just take the attendance or students they may go through example 1.6. Okay, let me take. So download the attendance. Okay, so I have now downloaded the attendance. Thank you very much for your time, and we will meet in our next lecture. Assalamu alaikum.
वालेकुम सलाम सर।